So he tells us the reason why they believe that is true, or they believe that it's in the right approach, is because of the beauty and elegance of these theories, right? And clearly a beautiful theory cannot be wrong, right?
Well, I mean, E equals MC squared. That's all you need to blow up the world or go really, really fast.
Yeah, or, in that case, not beautiful. He says, we might wonder why physicists would be so enthusiastic about a theory that has no empirical confirmation as yet, right? That we can't test or anything. Well, one reason is that string theory promises to be extremely elegant and beautiful, right? And there's a good precedent for these virtues, right? That is beautiful, elegant theories. After all, Einstein developed this theory, as you mentioned, E equals MC squared, and relativity and that kind of stuff. And the reason why Einstein pressed these theories and finally, they won the day to a certain extent, is because they were so elegant and so they were so beautiful, and so they had to be right?
Sure. Why not? I mean, 10 to the 500th power, you got to start somewhere.
Yeah, that's
so
right.
Beauty and elegance sounds like just the peachy keen first step.
And so these theories that we can't test empirically seem to be so beautiful, but one physicist blames this beauty approach and elegance approach on Einstein. He says, unfortunately, Einstein himself bears a lot of responsibility for having brought about this state of affairs in the fundamental physics. He became more mystical and started to believe that mathematical beauty alone, rather than experimentation, could point scientists in the right direction, right? Regretfully, when he discovered general relativity, employing this strategy, he succeeded. And this experience spoiled him for the rest of his life, right? So it is mathematically beautiful, so it has to be right. It has to map onto nature, right? And indeed, that's what Einstein found. He worked out the math, and the math was elegant, the math was beautiful, and we found out that indeed it mapped onto nature.
Right.
And so these theories do the math, they seem elegant, they seem beautiful, so they have to be right.
Yeah,
right?
Unfortunately, that's also what we saw with Newtonian mechanics.
Yes.
We saw them talk about how beautiful and elegant and precise and just how great this was. In fact, Newton then even went on to continue to have that mystical understanding of the spheres and trying to prove it while uncovering for them kind of the secrets of the universe, where he was coming up with the ability to do calculus, and again you do it and it works and it's great, and you take what you learned in math class, you tie it over to physics, and the bouncing ball matches exactly what you learned in your math class, and you're like, this is amazing, this is I'm learning math now, and I'm going to say, when am I ever going to use it? Whenever I kick a ball or look at bodies in motion. This is great. And so then we just have to apply it and say, well, okay, but then there are issues with it, and then we find out it's not true, and then we have to come up with two competing theories that kind of hollow out the middle, but work great on both ends, but don't come together. They're the don't cross the streams. They just bad things come from it. You'll burn your face off.
So there is a catch though with string theory and math, and you know what it is? He says, unfortunately, there is no mathematical formulation of string theory. Oops.
Man,
right?
I thought that was like the test.
Yeah. The story of string theory is not easy to tell because even now we do not really know what string theory is. We know a great deal about it, enough to know that it's something really marvelous. We know much about how to carry out certain kinds of calculations in string theory, but we do not have a good definition of it, nor do we know what its fundamental principles are.
Right.
So there's no mathematical formulation of string theory. So oops, we kind of missed the boat here.
Yeah.